Good afternoon, students. Today we will be doing about pericyclic reactions 2. In this pericyclic reactions 2, we have already studied the three different types of pericyclic reactions. We have studied with electrocyclisations, cycloadhesions, and sigmatropic reactions. Now we are going to study about three theories which are going to explain these pericyclic reactions. One is the FMO theory, the other one is the ATS theory, also called as the PMO theory, and then we have the orbital correlation diagram. Okay, so these are the three theories which are going to explain about the three different types of the pericyclic reactions what we have studied. So we'll start with the first theory, FMO theory, also called as frontier molecular orbital theory. Now, according to this theory was proposed by a scientist by name Fukai. Okay, according to this theory, the frontier molecular orbitals are nothing but the HOMO and the LUMO levels. Now, you must be knowing what is a HOMO. HOMO is nothing but highest occupied molecular orbital, lowest unoccupied molecular orbital. Okay, now according to this theory, any reaction proceeding with a bonding interaction under a given condition is considered to be an allowed transition. Okay, any reaction which is proceeding with an anti-bonding interaction is considered to be forbidden. Now, we know that the pericyclic reactions take place under two conditions. One is a thermal condition, the other one is a photochemical condition. Now, thermal condition, as I have already told you, thermal condition is considered to be taking place at a ground state. So, thermal condition, we need to always consider the ground state, whereas for a photochemical condition, we need to consider the first excited state. Okay, now using all these instructions or using all these guidelines and using the FMO theory, we are going to use it initially for the first set of the pericyclic reactions, that is nothing but the electrocyclisations. Okay, so coming to the first one, that is the electrocyclisation. Now, electrocyclisation. Now, what is a characteristic feature for the electrocyclisation? Whenever we see the electrocyclisations, I told you, they are reversible reactions, correct? And they involve only one single molecule. So I can call them as intramolecular reactions. And obviously they are pericyclic reactions, so they are concerted reactions. Now, when we are talking about intramolecular reactions, it's a single reaction. So here we need to consider only the one level, that is the HOMO level only we are going to consider. Why only the HOMO level needs to be considered? Because only one molecule is involved. Since only one molecule is involved, we are going to consider only the HOMO level. Okay. Now, coming to the first condition, that is the thermal condition. Under the thermal condition, you need to consider the HOMO of the ground state. What state? HOMO of the ground state. Now, when I'm going to take a photochemical condition photochemical condition involves the HOMO of the first excited state, right? So HOMO of the ground state and HOMO of the first excited state. Now, coming to the electrocyclization, we know what is a 4n pi system. Okay, so 4n pi system in electrocyclizations is 1,3-butadiene. So this 1,3-butadiene is drawn in this way. Reaction, it's a reversible reaction giving rise to your product, which is nothing but your cyclobutene. Now, in this reaction, when we are going to see how many sp2 hybridized carbons we have one, two, three, four. So we have 4 sp2 hybridized carbons. So we expect 4 psi functions and 4 molecular orbitals. Okay, we have constructed all these orbitals in the first unit. Now, why I am going to insist on this one is, now we need to see what? We need to see the ground state and we need to see the first excited state. So, make a column like this, wherein you are going to show the psi functions. Okay, now, when you all are going to show the psi functions, how many molecular orbitals you have? You have 4 molecular orbitals. Psi 1, psi 2, psi 3 and psi 4. So this is psi 4, psi 3, psi 2, psi 1. Similarly, psi 1, psi 2, psi 3, psi 4. Right? Now, we are going to take it for the, this will consider it to be the ground state, and this is the first excited state. How many electrons do we have? We have 4 pi electrons. Each molecular orbital can accommodate 2 electrons. So 2 electrons are here. In the first excited state, the psi 1, one of the electron moves into the higher energy orbital. So ground state, the HOMO of the ground state highest occupied molecular orbital is psi 2. First excited state. For this one, you have HOMO of the first excited state, highest occupied molecular orbital. Whether it is occupied by a single electron or whether it is occupied by 2 electrons, it is considered to be occupied. So what is being occupied here? The highest one is psi 3. So HOMO of the first excited state is psi 3. Okay. Now what we are going to do is, for a 4m pi system, we are going to apply the FMO theory. Now what do you need to consider? FMO for the thermal condition, you need to consider the HOMO of the ground state, whereas under the photochemical condition, you need to consider the HOMO of the first excited state. In electrocyclizations, we have another characteristic feature, which is the directions in which the molecule is going to rotate, so that you get a cyclobutane. So this one, we have 2 types of rotation. We have con mode of rotation and we have a dis mode of rotation. So using both these methods, using either the con mode of rotation or the dis mode of rotation, you will be getting the product. But under what condition con mode of rotation is said to be possible, and under what condition the dis mode of rotation is possible, we will be seeing it. Now, let us go to the first one, that is a con mode of rotation for a 4n pi system. Now, you already know that for the HOMO of the ground state, I'm going to write it here. HOMO of the ground state is side 2. This is for the 4 and 5 system. Okay, whereas HOMO of the first excited state is side 3. You should be remembering these to write down here. Now, 4 and 5 system. Right? Now, I'm going to write the same psi2 function. Psi2 function, how many nodes does it have? It has one node. Okay, so write the molecule in the same way. Draw the p orbitals. This is the p orbital, right? Okay. Now, how many nodes does it have? It has one node. Imagine that this is the node here. So it is plus, plus, minus, minus. Okay. Now, rotate it in a con mode of rotation. Now, I'm going to take it. This is under thermal condition. Okay. So, con mode of rotation, both of them in the clockwise direction. Catch the upper part of the lobe and rotate it in this way. Similarly here, rotate to your right hand side. Now what will happen when you are going to write a cyclobutene? The p orbitals are going to be overlapped in this way. Okay, so when you find it, what has a negative sign? It comes outside. What about the positive? It comes inside. Similarly, positive is inside, negative is outside. Now what are you getting? You will be getting a bonding interaction. So any bonding interaction is considered to be allowed interaction. So it is a bonding. Bonding is considered to be allowed. Clear? Now, I'm going to take the same con mode of rotation in an anti-clockwise direction. Okay? Con mode of rotation in an anti-clockwise direction. That I'm going to put it in a reverse way. Both of them, instead of moving to the right hand side, they will be moving to the left hand side. Formation of the cyclobutene, both the p orbitals will be rotated. Now, if I'm going to rotate it left hand side, my positive sign will be coming outwards, negative is inward. Similarly, negative is inwards, positive is outward. Whenever it is a same sign overlap, then it is always a bonding interaction. So here again you are getting a bonding interaction. So whenever you're getting a bonding interaction, it is considered to be a allowed interaction. Clear? Now, for the same 4 and 5 system, I have two modes of rotation. I told you con and dis mode of rotation. For the same molecule, go for a dis mode of rotation. So, I've already shown here, I'm going to draw the same molecule. We'll go for the dis mode of rotation. In the dis mode of rotation, we find one molecule is being rotated in a clockwise direction and the other molecule in an anti-clockwise direction. Okay, so in this one, so please draw the cyclobutene structure. P orbitals. You find the p orbitals in this way. Now, if one is being rotated in this one, the other has to be rotated in the other direction. If I'm rotating, negative is outside, positive is inside. Similarly, positive is outside, negative is inside. Since it is opposite signs overlap, these interactions are called as the anti-bonding interactions. All anti-bonding interactions are considered to be forbidden. So, from this, I can conclude that for a 4 and 5 system, under thermal condition, con mode of rotation is allowed whereas this mode of rotation is considered to be forbidden. Is it clear? Now, we'll go for the next one. We'll take the photochemical condition. For the photochemical condition, I have told you, for the photochemical condition, we need to consider the excited state. Okay. Photochemical condition, because it is a light, consider the HOMO of the first excited state. What is the HOMO of the first excited state? Site 3. Okay. So site 3 you are going to give it. Write the molecule. Site 3. Site 3, I am going to write the molecular orbitals. Construct the molecular orbital. So site 3, how many orbitals? Since I have 4 sp2 hybridized carbons, 1, 2, 3, and 4. How many nodes do I have? Site 3. So 2 nodes. I'm going to put one node here and another node here. Place the signs plus, minus. Why? Because I have a node here. Do I have a node here? No. So the same sign, again it is a plus. So minus, plus, plus, minus. The same thing I am going to orient in for 1,3-butadiene structure. Okay. Now, we are going to make use of only the termini p orbitals. Why? Because the termini p orbitals are going to overlap to give you the bonding interaction. Okay, and they are going to close the structure to give you a ring. Now, for this one, do con mode of rotation. Now, I have already told you con mode of rotation is a same side interaction. Okay, so rotate it along your right hand side. When you are rotating it along your right hand side, what do you find? These are the p orbitals. Okay, now plus is inside, negative outside. I have negative inside and positive outside. What has happened? Now, what I am getting a anti-bonding interaction. So, if it is anti-bonding interaction, it is considered to be forbidden interaction. Now, next one. Do again another con mode of rotation. Now, both of them I'm going to rotate in an anti-clockwise direction. If you're going to rotate it in anti-clockwise direction, draw the p orbitals. These are the termini p orbitals, right? Now these termini p orbitals, so positive outside, negative inside, right? Again, positive inside, negative outside. Again, it is opposite sign. Again, it is an anti-bonding interaction. If it's an anti-bonding interaction, it is considered to be forbidden. Now we have finished with the con mode of rotation. For the same molecule, I'm going to do this mode of rotation. Okay. Now this mode of rotation, one is in a clockwise direction, the other one is in an anti-clockwise direction. Draw the molecule, right? Now one I am going to rotate it in a clockwise direction. So plus comes outside, negative is inside. The other one I am going to rotate in an anti-clockwise. Plus outside, negative inside. I'm getting a bonding interaction. So bond is taking place here. So whenever a bonding is taking place, it is considered to be a allowed interaction. So this is a bonding interaction and this is allowed interaction. Clear? Okay. Now we have finished with the 4n pi system. So according to the 4 and 5 system, the conclusion what we can draw is for a 4 and 5 system, Hahn mode of rotation was thermally possible. This mode of rotation is photochemically possible because we are getting a bonding interaction. Okay, now we'll go to the next one, that is a 4n plus 2 pi system. 4n plus 2 pi system. So 4n plus 2 pi system here is 135 hexa triene. This is your molecule. 1, 2, 3, 4, 5, 6 hexa triene. So 1, 2, 3. 1, 2, 3. 3 bonds you have. This molecule also undergoes a reaction, electrocyclisation, to give you a closed structure at the expense of one pi bond. One new sigma bond is said to be formed. Now, since I have 6 sp2 hybridized carbons, I expect 6 psi functions. Now, I'm going to write the 6 psi functions in the same picture what we have drawn for the 4 and pi system. Psi 1, psi 2, psi 3, psi 4, psi 5, psi 6, right? Psi 6. This is for the ground state. Then we take it for the first excited state. Again, psi 1, psi 2, psi 3, psi 4, psi 5, and psi 6. Now, each psi function can accommodate only 2 electrons. So the 2 electrons, how many electrons do I expect to have? I have 6 electrons. So we are going to take only the reactant molecule. 1, 2, 3, 4, 5, 6. So the HOMO under the ground state here is psi 3. Similarly, we are going to take the first excited state. One of the electron from the psi 3 moves into psi 4. So the remaining all are going to remain same. One is going to move here. HOMO of the first excited state will be psi 4. Why are we considering only HOMO? Because it is only one single molecule which is participating in the reaction. Okay. Now, I'm going to write all these conditions here. So, HOMO of the ground state is psi 3 and HOMO of the first excited state is psi 4. Right. Now, take it for the thermal condition. Now, under the thermal condition, you need to take the HOMO of the ground state. HOMO of the ground state is psi 3. I'm going to draw the molecule first, the molecular orbital in a straight line. 2, 3, 4, 5, and 6. Psi 3 has 2 nodes. So you can put 1 and second node here. Plus, plus, minus, minus, plus, and right. Now the same one I'm going to construct in this way. We should be concerned only with the termini p orbitals. The termini p orbitals will be at the corner. Now, what does the corner signs have? Both of them are having positive, positive, negative, negative. Okay. Now, the rest of the molecule, the rest of the p orbitals are not being concerned here. Why? Because it is only the overlap of this one gives you the closure of the ring. The rest of them are going to redistribute themselves. Now, what we need to consider, again, it's an electrocyclization reaction. We need to consider the con and the dis mode of rotation. Do the con mode of rotation. For con mode, both of them are in a clockwise direction. Rotate them in a clockwise direction. Your molecule, the termini orbitals. Now, I have the positive sign outside, negative is inside, positive inside, negative outside. I'm getting opposite signs here. Again, it's an anti-bonding interaction. All anti-bonding interactions are forbidden interactions. Again, go for the another con mode of rotation. Now this con, both of them will be doing in the anti-clockwise direction. So when you're doing it in an anti-clockwise direction, negative inside, positive is outside. Again, positive comes inside, negative is outside. Again, it is an anti-bonding interaction. So whether you are going to take it in a clockwise or whether you're going to take it in an anti-clockwise direction, you are getting a anti-bonding interaction which is a forbidden. Now, for the same molecule, go for the dis mode of rotation. In the dis mode of rotation, you find one of them to be rotated in an anti-clockwise direction and the other one is in a clockwise direction. So when you're going to draw it, you find the termini p orbitals in this way. Okay, so positive outside, negative inside, negative inside, positive outside. It's a bonding interaction. If it's a bonding interaction, then it is considered to be a allowed interaction. So this is bonding, which is considered to be allowed. So what condition we have done it? Under the thermal condition. We have one more condition, that is the photochemical condition. Okay. For the photochemical condition, we need to consider the HOMO of the first excited state. What is the HOMO of the first excited state? Psi 4. So go for the photochemical condition. Psi 4 is my orbital. Psi function. Draw the 6 molecular orbitals. 1, 2, 3, 4, 5, and 6. How many nodes do I have? I have 3 nodes. So one node here, another 2 nodes here. So this is plus, minus, minus, again plus, plus, minus, plus, minus, Okay. Now, this is in a straight line. I'm going to draw it in a molecular way. Okay. So, this is your draw only the termini p orbitals. Right. Now, this termini p orbitals, what signs do I have? I have plus on top and negative here for the termini. Okay. Now, for this molecule, again do a con mode of rotation, and this con mode, both of them are in a clockwise direction. So when you are doing it in a clockwise direction, rotate them. What are you finding? When you rotate them, you find negative is outside, positive is inside, positive inside, negative outside. This is considered to be a bonding interaction again. So it has given rise to a bonding interaction again, which is considered to be an allowed interaction. Now, I'm going to take for a this mode of rotation. So, con mode of rotation, both of them in an anti-clockwise direction. Okay, when I'm going to take an anti-clockwise direction, again project the p orbitals. When you are projecting the p orbital, negative is inside, positive outside, again negative inside, positive outside. Since it is the same sign overlap, it is considered to be a bonding interaction. All bonding interactions are considered to be allowed interactions. Now, for the same molecule, I'm going to do a this mode of rotation. So when you're going to do a this mode of rotation, one is in a clockwise direction, the other is in an anti-clockwise direction. Again, the terminal p orbitals, right? The terminal p orbitals, here you will be having minus outside, positive inside, again negative inside, positive outside. Both of them are opposite signs, so you will be getting a anti-bonding interaction. So if it is an anti-bonding interaction, this is considered to be forbidden. Okay, now using these, we are going to prepare a table, what we call it as a selection rule. So successfully we have explained the FMO theory for the electrocyclisation, that is the first set of reactions. So for this first set of theory, please write down selection rules. Under these selection rules, the serial number, type of pi system, then mode of rotation, what is allowed, forbidden. Serial number 1, type of pi system, 4n pi system. What is the 4n pi system? 1,3-butadiene. Under this one, the con mode of rotation. Con mode of rotation, when we have seen, it was thermally allowed, but it was photochemically forbidden. Whereas the dis mode of rotation was photochemically allowed, but thermally forbidden. We find that if con is allowed under thermal condition, then the photochemical condition, it is forbidden. If it is allowed under photochemical condition, then it will be forbidden under the thermal condition. So any condition, whether it is a con or this mode of rotation, will be taking place only under either thermal or photochemical, but never both of them. Okay. Next, the second one, we have 4n plus 2 pi system. 135 hexatriene. Again, for this molecule, again go for con mode of rotation. Under this con mode of rotation, was considered to be photochemically allowed but thermally forbidden. Then your dis mode of rotation is considered to be thermally allowed but photochemically forbidden. Just the opposite of it. This is the simplest way in which you can remember your FMO theory. This is a shortcut form, or what we call it as a selection rule. When a question is being asked, explain the electrocyclisations based on the FMO theory, then you need to write all the previously, how you have come to this conclusion, what you have considered, and what HOMO levels you have considered. Okay, thank you.